Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about a complete design of simply supported one-way slab. You know what do you mean by one-way slab is? One-way slab is if Ly by Lx is greater than 2, then we can design it as a one-way slab. In this, Ly is nothing but the longer span of a slab, Lx is nothing but a shorter span of a slab. The ratio of these two, that is Ly by Lx, is greater than 2, then we can design it as a one-way slab. And if this slab is supported by a two simple support or two simple walls, parallel walls, then we can call it as a simply supported one-way slab. For this simply supported one-way slab, we have to design by using limit state method as per IS 456-2000. So let us discuss what are the outcomes of today's class. So after completion of this class, you will be able to design by your own a complete design of simply supported one-way slab. Right? How to design this? We know what are the basic steps we can use for designing of any kind of slab. By using those steps, we can design this simply supported one-way slab. So let us recall what are the things we have discussed in previous class. That is step-by-step procedure for a one-way slab. So what are the steps we have here? Effective depth, effective length, load calculations, factored bending moment calculation, minimum depth required calculation, area of steel. After calculating all these parameters, we go for check for deflection, shear and development length. Say what we'll do in effective depth. Here the effective depth of a simply supported beam can be calculated based on the stiffness criteria. So there is a provision given, that is D equal to span by basic value. That basic value may remain for simply supported beam, that is 20 to 30, or sorry 25 to 30. And effective length of a simply supported beam can be calculated. We have two criteria. One is center to center distance between the support, or another criteria is clear spans plus effective depth. The minimum of these two value we consider as a effective length of that. And load calculation, here so many kind, like dead load we have, live load and some finishes. By adding all together, we calculate total load, and multiplying the total load with some suitable partial factor of safety, we will get factored load is. Here dead load will be calculated by using given dimension, like dead load is nothing but self weight of the member. After calculating dead load, live load and finishes and total load and factor load, we have to calculate what is the factored bending moment is. You know, as we are calculating simply supported beam means the factored bending moment will be WL square by 8. So after calculating factored bending moment, we have to calculate minimum required depth. What do you mean by minimum required depth? For a given dimension, for a given loading condition, what minimum depth is required for particular element. Say here we are designing slab, so what minimum depth required for slab to withstand the load which are applying on the slab. So this can be calculated by equating factored bending moment with your limiting moment of resistance. From that we will calculate what is D is. So this D can be obtained, this D can be compared with already the depth assumed or calculated in first step. From that, if we are getting the assumed depth is more than the minimum depth required, we can adopt the assumed depth as a total effective depth for given slab. If it is less than that, the minimum depth required will be adapted as a depth required for particular slab. And then we have to calculate area of steel. For calculating area of steel, we have a codal formula, that is mu. This can be calculated with respect to the moment of resistance formula in tension zone, or with respect to steel, that is mu equal to 0.87 Fi AST in D into 1 minus Fi AST by FCK into BD. From that formula, we can calculate what is the area of steel is. So these all steps are related to your design step. Then we have to go for check against deflection, whether it is safe against deflection, or it is safe against shear or not, and safe against development or not. Those we have to check with respect to the obtained values. So by using these, by having the knowledge of all these steps, then it will solve or it will design one a numerically a simply supported one-way slab. So let us take one problem here. Design a simply supported roof slab for a room 7.5 meters by 3.5 meters, clear in size. So it is a clear span. Yeah, is supported on 230 mm width. What is the width? That means the width of the wall or on which support is supporting. That is a 230 mm. The slab is carrying imposed load of 5 kN per meter square. Use M20 concrete and Fe 250 steel. See, from this problem, it does not mention that what type of slab we have to decide. First of all, we have to decide what type of slab we are going to design. And then we have to design on which support is mounted on. As it is a cantilever slab, or it is a simply supported slab, or it is a continuous slab. In the problem straight away is given that design a simply supported roof slab. So we have to design a simply supported roof slab. So why I am mentioning here means we have to, while we are calculating the factored bending moment and factored shear force, the formulas or values will be differ for type of slab. That means value differ from simply supported slab to the cantilever slab and continuous slab, like that. That's why I'm mentioning and stressing the type of slab is. So simply supported slab, these are the dimension, and it is supported over a 230 mm width. This will be helpful you when we are calculating effective length of the slab. And it is carrying a imposed load. This imposed load also call it as a live load, right? And we have to use M20 concrete and Fe 415. So let me decide that what type of slab we are going to design. We know that based on the support condition, we have to design a simply supported slab. In simply supported slab, whether we have to design one-way slab or two-way slab, that we have to decide here. Say here the size of the room is given is 7.5 meters by 3.5 meters. 7.5 meters is the longer span and 3.5 meters the shorter span. So generally a 7.5 meters longer span designated with a Ly. So I can write longer span is equal to Ly is equal to 7.5 meters. And shorter span 3.5 meters can be written as shorter span is equal to, it is in the shorter direction, that is the x direction. So Lx equal to 3.5 by 3.5 meter. So to decide the type of slab, whether it is a one-way slab or two-way slab, we have to check the ratio between longer span to the shorter span. So now calculate the ratio between longer span to shorter span, that is Ly by Lx equal to 7.5 is the longer span by 3.5 the shorter span. The value obtained is 2.14, which is greater than 2. So we know that for definition of one-way slab and two-way slab, a slab said to be a one-way slab when the ratio of Ly by Lx is greater than 2, we can call it as a one-way slab. So from this problem we obtain this ratio, that is Ly by Lx is greater than 2. So hence this slab is to be designed as a one-way slab. So we had decided from this step that we had to design simply supported slab as a one-way slab, right? So for that we have some steps here. We have to follow these steps and we'll calculate or we design a simply supported one-way slab. So these are the given data. He has mentioned that in the problem he has given two dimensions, that is Lx and Ly. Generally for calculating effective length of the beam, as we are designing one-way slab, our maximum concentration have to pay on shorter direction of the slab only. So with respect to the shorter direction only, we have to calculate effective length of the slab, because the maximum amount load will carried by shorter span and maximum bending moment will occur along the shorter direction only. That's why we have to pay attention on Lx only. So the clear span given in the shorter direction we have to consider, that is Lx equal to 2.5 meters and wall thickness given is 230 mm. Live load is given is 5 kN for mm square. It is nothing but a imposed load, and FCK, that is M20 grade of concrete means it is a characteristic compressive strength of a concrete, that is 20 Newton for mm square. And similarly as given the grade of steel used, Fe 415 steel, that is Fy equal to 415. That is a characteristic strength of a steel, or I can say yield strength of a steel. Fy is equal to 415 Newton for mm square. So by decided type of slab and given data, we have to design our simply supported one-way slab. So let me start with the first step. First step in this for design of simply supported one-way slab is we have to calculate effective depth of the slab, or I can call it as a thickness of the slab. So this can be calculated the effective depth by assuming suitable depth based on the stiffness criteria. According to the code, the stiffness criteria can be calculating effective depth of one simply supported slab is, that is L by D ratio is equal to, it will vary from 25 to 30. So we want what is the effective depth is, and these are the basic value. So effective depth is equal to span by basic value. So for this I am considering basic value is 25. So this can be calculated in other way also. That is effective depth can be calculated. Your basic value generally considered simply supported beam 20 and multiplied by that value must be multiplied with some modification factor. So you can assume, so for a modification factor from 1.5 to 2. From that also we can calculate effective depth is. So this see effective depth span by basic value multiplied by modification factor, that will give these 25 to 30 value only. Both are remain same. So here I am calculating effective depth equal to span by, I am choosing the basic value between these two. So more specifically I am taking basic value of this is 25. So if I calculate the effective depth with respect to this, the effective span given is 3500, that 3500, that is Lx by 25 is my basic value. From this I will get small d, that is effective depth is 140 mm. It is assumed generally for the based on the experience we have calculated all this value, but whether this value is appropriate or not, we have to decide when what is the minimum depth required for a slab. We have to check this value and minimum depth value, then we can decide what value we have to provide for as a effective depth, right? Next, so for this I have to adopt a clear cover 20 mm and I am using 10 mm bar, and clear cover is 20 mm, bottom clear cover is 20 mm and using 10 mm bar. This bar should not be chosen blindly. You know the one criteria that the maximum diameter of bar can be provided in the slab is 1/8 of a thickness of the slab. Maximum, but that maximum diameter of can be provided in the bar is 1/8 of a thickness of the slab. So according to that you have to calculate what maximum you can provide, or 12 will not provide more than 12 mm bars in a slab, right? So here based on that criteria I am using 10 mm bars. So from that I can calculate what is the total depth is. You know the total depth or overall depth can be calculated effective depth plus clear cover. It is not effective cover here. Clear cover plus half of the diameter of bar, that will give me the total depth. Say that equal to effective depth assumed is 140 based on the stiffness criteria, and plus the clear cover is 20 and half of the diameter nothing but 10 by 2. The overall depth of the slab will be termed as 165 mm. So from this step I have calculated what is the effective depth and what is the overall depth. Effective depth equal to 140 mm and overall depth equal to 165 mm. So after calculating this step, we have to go for second step, that is calculation of effective span according to the clause number 22.2 of IS 456-2000. As we are designing, it is simply supported one-way slab. The effective depth can be taken as minimum of criteria A and B. What is the criteria A? It is a clear span plus effective depth of the slab, and criteria B is center to center distance between the support. So we will calculate the effective span length based on these two criteria, and after obtaining the values based on these two criteria, we have to choose the effective span as minimum of these two criteria. So let us calculate with respect to first criteria, that is clear span plus effective depth. What is the clear span is given? That is 3.5. Simply it is a shorter direction of the slab or shorter length of the slab. That is 3.5, and we know effective depth of the slab is So this is 0.140, 0.145 say, and a center to center distance between this is 3.5 plus the support width is 0.23. What is support width? 0.23. Altogether you will get 3.730 meters. Right? Hence the effective span is 3.645. A minimum of this, it is 3.645 and a 3.730. The minimum of this is 3.645 meters will consider as a effective span. Right? Then after obtaining the effective span, we have to calculate the total load or what are the loads which are acting on the particular slab. So by considering 1 meter width of the slab, we are not considering whole width of the slab, we are considering 1 meter width of the slab, we are calculating total loads. So the first one is dead load, that is the self weight of the slab, that is overall depth multiplied by 1 meter length and 1 meter width multiplied by unit weight of the slab we can consider, that is 0.165 into 25 is equal to 4.125 kilonewton per meter square. So this is the self weight of the slab, or I can say it is a dead load which is acting on the slab. And one more type of load given, that is the imposed load, or I can call it as a live load, that is given in your problem, that is equal to 5 kilonewton per meter square. Therefore the total load is equal to dead load plus live load. So W equal to 4.125 is the dead load plus 5 equal to, that is 5 is live load. Altogether if we add 9.125 kilonewton per meter square. Right. This is the total load which is acting on the slab, but we have to calculate what is the design load is or the factor load is. That can be calculated by using some suitable partial factor of safety when we are using combination of dead load and live load with respect to limit state of collapse in flexure condition, that equal to, therefore factor load W is equal to 1.5 times total load. So 1.5 times the total load is 9.125. From this if you multiply that factor load will get is finally 13.68 kilonewton per meter square. Okay, then we have to calculate what is the design moments, or I can say factored moments. As we are designing simply supported beam and the simply supported beam carrying a UDL throughout, then what will be the maximum bending moment will occur. This formula we can derive from your concept of strength of materials in shear force and bending moment topic. When you simply supported beam subjected to UDL throughout, then the maximum bending moment will occur at the center of the beam, that is WL square by 8. In place of W, we are using here a factor load, that is W. Finally, the maximum bending moment or ultimate bending moment or factored bending moment, Mu is equal to WL square by 8. Already we have calculated what is the W is. So from that, Mu equal to W is 13.68 and this is the effective span, that is 3.645 square by 8. If you multiply all together or divide by 8, we will get Mu is equal to 22.71 kilonewton into meter. So this is the ultimate moment or ultimate design moment which can likely to occur on the slab. So based on this, we have to design all our dimensions of a slab, right? So to restrict this moment, so what is the minimum depth of slab required? The minimum effective depth of the slab required, that we have to calculate. So the calculation of minimum effective depth required, this can be calculating by equating the maximum bending moment to the limiting moment of resistance of a section. The maximum bending moment is this one, the value which is obtained, that this much maximum bending moment likely to occur on our slab. And what is the limiting moment of resistance of a given section? So that is Mu is equal to K into FCK BD square. This formula already we know when we are deciding singly reinforced beam and doubly reinforced beam. Right? The design of slab is as similar as your design of a beams. So we have to equate the maximum or design moment is equal to limiting moment of resistance. From this, mu is equal to limiting moment of resistance. We have a formula K equal to FCK into BD square. This K value depends upon the grade of steel. So from this, if we rearrange the term, we required what is a D is. Here D is nothing but effective depth required for a slab for resisting this maximum bending moment is equal to under root of mu by K FCK into B. Right? The K value depends on grade of steel, as I told you. That is for Fe250, the grade of steel and the K value will be 0.148. For Fe415, the grade K value will be 0.138, and Fe500, the K value will be 0.133. And delete this value, is some other value. Okay. From this, small d is equal, if you substitute all these values in this equation, that is under root of mu is nothing but already we have calculated 22.71 kilonewton into meters, and that value we have to convert into newton into mm. Then you have to multiply that 22.71 with a 10 power 6. Here we have a 10 cube and 10 cube. One 10 cube is for converting kilonewtons to newtons, and another 10 cube is for converting meter into mm. That's why we are multiplying here your factored bending moment with 10 power 6, right, by 0.138 into FCK. Grade of concrete is 20 is given, and we are designing the everything, either dimensions, depth, or the reinforcement with respect to 1 meter width of the slab. That is 1 meter nothing but 1000 mm. So for this case, the minimum depth required, that is minimum effective depth required for a slab is 66.2 mm. 66.2 mm. But assumed depth will be 140 mm. How much? 140 mm. So our this is a wrong calculation here. If you calculate with respect to this, we'll get the minimum depth required is 90.71 mm. So the 66.2 is the calculation of other problem. So just dear students, make it correct here. So it is not a 66.2 mm. It is a 90.71 mm. Okay. This value is less than, what is that? Our assumed value, the value effective depth calculated with respect to the stiffness criteria, that is 140 mm. So the effective depth required is less than the provided. So use provided depth go for the further steps. So make it clear here, it is not a 66.2 mm, it is 90.1 mm. My dear students, please make it correct. This is a some topographical mistake or a copy paste mistake. Right. Next, we have to calculate the area of steel by considering 1 meter width of the slab. Okay, how to calculate this? As I already discussed you, the area of steel we have to calculate with respect to the moment of resistance in tension zone, that is mu equal to 0.87 Fy AST into D into 1 minus a Fy AST by FCK into BD. If you substitute the values here, mu equal to 17.84 into 10 power 6. And finally, we will get AST equal to, that is 483.27 mm square. 483.27 mm square. If you simplify this equation, right? And here mu is not, it is not a correct value. Mu is 22 point here. Again, this is a copy paste mistake. 22.71 into 10 power 6. Please, students, correct it. This is a 22.71 10 power 6. So it is from, if you calculate that, we'll get AST value is 483.27 mm square, right? So we have to now, after calculating area of steel, then whether we are approaching or we are satisfying the criteria called a minimum reinforcement provided. So according to the codal provision, that is IS, according to IS 456-2000, if you are using Fe41 steel and Fe415 steel, the minimum reinforcement should be provided that equal to 0.12% of gross cross-sectional area. So that is 0.12 by 100 multiplied by B. B, we are using it as a what? 1 meter width, that is 1000 mm, and overall depth we have obtained is 165. If we calculate that with respect to this, we will get AST minimum provided is 198 mm square. But AST is 483, so our AST minimum is less than AST obtained. So hence we are safe against the minimum reinforcement. and I am using here 10 mm diameter bars. For that, I want to calculate what is the spacing for 1 meter width of the slab. What is the spacing I have to provided for a main bars. So S equal to spacing, that is small AST by capital AST into 1000. Here small AST is the area of 110 mm bar. If we calculate that, AST equal to pi by 4 into 10 square. If we calculate this, we will get the area of 110 mm bar is equal to 78.5 mm square. Now substitute this AST value, small AST value and capital AST value, then we'll get what is the spacing to be provided. So that is S equal to AST by small AST by capital AST whole multiplied by 1000. Small AST equal to 78.5 by capital AST equal to 483 whole multiplied by 1000, then we'll get 162.3 mm. But this is the obtained value. Whether this obtained value is fulfilling our criteria or not, that we have to check. So as per our IS 456-2000, spacing of the main steel should not be more than 3 times D and 300 mm, whichever is less. So if you take the 3 times D, that is 3 into 120, that is 360 mm and 300 mm. So minimum of these two value we have to consider, but we have to check now obtained value and from these two criteria's value. We have to take the minimum value of all these three criteria's now. The minimum of these three criteria's, we can take it as a spacing for the main reinforcement. So among these, this 162.3 mm is the minimum. So I will provide 162.3. So I will round it to provide a 10 mm bar at 160 mm center to center. And when you are providing these bars, we have to these bars should be bent alternate at the face of the support. There is a distance of 0.1 into L meter from the face of the support, as similar to your beams. So this is all about your calculation of steel for main reinforcement and spacing of the main reinforcement. Let us check the distribution reinforcement. You know, we have to provide distribution reinforcement in the one-way slab along the LY direction, that is a longer span direction. So there is no particular maximum we can provide like this, or that is, if you provide the minimum reinforcement, that itself a self-sufficient for the distribution reinforcement. So you know, for FE 4 and 5, the minimum reinforcement provided for the as a distribution reinforcement is 0.12% of gross cross-sectional area. So from this I can calculate what is the area of steel provided in a distribution reinforcement. The 0.12 by 100 into 1000 multiplied by 165. From this, AST minimum equal to 198 mm square. If you calculate this value, the AST minimum will be obtained this 198 mm square. So here we have to use the diameter of bars varying from if you are using a Fe 415 steel, then the diameter of bar should be used as a distribution reinforcement varies from 6 mm to 8 mm, but I am using here 8 mm diameter bar. For this particular case, what is the spacing we have to calculate? As usual, the spacing can be calculated S equal to small AST by capital AST into 1000. Small AST is the area of 1 8 mm diameter bar. That will be AST, small AST equal to pi by 4 into 8 square. We'll get 50.24 mm square. Right, from that, substitute the small AST value and capital AST value in this equation. We'll get, that is 50.24 by 198 whole multiplied by 1000. The spacing will be obtained from this formula 253.73 mm. For there is also codal recommendations. We should not violate the codal recommendation. So whether obtained value are well within the codal limits or not, that we have to check. So as per IS 456-2000, the spacing of distribution steel should not be more than these criteria, that is 5D and 450 mm. So if we calculate 5D, we will get 5 into 120, that is 600 mm, and 4, it is not sorry, again it is a 120, it is a 140, we will get something 720 odd, and it is a 650 mm. From these three values, that is 1, 2 and 3, we have to calculate minimum of these three values as our spacing for the distribution reinforcement. So this value is 253.73 mm, and but rounding out to spacing is 250. Hence, provide 8 mm bars at 250 mm center to center. So these are the design of your beam with respect to slab, one-way slab with respect to limit set of collapse and flexure condition. So what we did so far, we have calculated D and we have assumed B, that is 1000 mm. Then we have calculated area of steel, and what is the area of steel are self-sufficient or not, that we have checked with the minimum area of reinforcement provided, and what is the spacing to be provided for the bar also checked. So that is a part of a design. Whether designed amounts or design parameters are safe against some parameters like deflection, shear and development length, that we have to check now. So we go for check against the deflection. This can be calculated by obtaining percentage of steel and by knowing the stress in steel under the service load. The percentage of steel can be calculated, that is 100 AST provided by BD. Here I am providing 483 mm square as a steel, that is 100 into 483 by 1000 is your 1 meter width of the slab, and D is 140 mm, that is the effective depth of the slab. Now if I calculate, we will get, that is percentage of steel obtained from this is 0.345 percentage, right? And we have to calculate stress in steel under service load by using this formula. Fs is equal to 0.58 Fy into AST required by AST provided. As required and provided both are same, I am assuming like that. And this formula you can get from IS 456 2000 in the table that I will show later. That is 0.58 into 415, that is 481 by 483 by 1. Finally, we will get the stress in steel under the service load will be 240 Newton per mm square. Right. After obtaining Fs value, Pt value, we have to calculate the modification factor is. Right. The modification factor can be calculating knowing the percentage of steel and the value of Fs. So the percentage of steel we obtained is 0.345. So here on x-axis we have a percentage of steel here, and that is say it is 0.4, and somewhere I have say 0.345 here. Okay, and that is 240. So somewhere I will get approximately here. According to that, I want to calculate what is the modification factor is, and the curve is 240 Newton per mm square curve we have to see. So this is 0.4 percentage of steel. So I am assuming that is 0.35 percentage of steel, corresponding value we have to take on 240 Newton per mm square. Say here that will intersect here in this curve, and if I project onto this, somewhere approximately I will get my modification factor will be 1.4. So you know, if a slab is said to be a safe against the deflection, it should fulfill the criteria, that is L by D maximum should be greater than L by D provided. L by D maximum should be greater than L by D provided. So L by D maximum can be calculated basic value multiplied by KT. This basic value depends upon the type of slab we are using and type of support condition. As we are deciding to design that simply supported slab, for simply supported condition the basic value will be 20, and the modification factor, that is 1.4. So if you calculate, that is 28. L by D provided is effective length of the slab to the effective depth of the slab. The effective length of slab is 3645 by 140, that is 26. So our L by D maximum is greater than L by D provided, we can say, hence our slab is safe against the deflection. So it is okay in deflection. So then we have to design our slab against the shear reinforcement. Whether slab is safe against the shear or not, that we have to check. Generally, slabs are safe against the shear as well as in development length. Anyhow, we have checked whether the given data whether they are safe or not. So as we are designing simply supported slab with uniformly distributed load, or we are assuming as a 1 meter width of the beam, and we are designing, so I can call it a simply supported beam with uniformly distributed load. The maximum shear force occurs in the support, that will be Vu is equal to WL into WUL by 2. Already we have calculated what is the WL by W factor load is, that is 13.68 into this effective length is 3.645 by 2. From that we'll get 24.21 kilonewtons. 24.21 kilonewtons. Say after calculating that, we have to calculate nominal shear stress. That the calculation of nominal shear stress, we have one formula based on the IS 456 2000, that is tau V is equal to VU by BD. Here VU we have already calculated 24.93 and this is in kilonewton, that will be multiplied by 1000, that will be converted into Newton, by B is 1000 and effective depth is 140. So altogether if we calculate this factor, then we'll get tau V, nominal shear stress tau V is equal to 0.78 Newton for mm square. See, you have to see one point here, whether your slab is safe against a shear, it has to fulfill the two criteria. One is the relation between tau V and tau C max, that is tau V must be less than tau C max by 2, one condition. Another condition is your tau V must be less than k times tau C. You know tau V is nominal shear stress, tau C max is maximum shear stress in concrete, and tau C is design shear stress in concrete. If you satisfies the those two conditions, then we can say our slab is safe against the shear. Now we'll check based on the data whether they are safe against the shear or not. So calculate the maximum shear stress, where this will be depend upon the grade of concrete. For a grade of concrete given is M20, from the tau C max is 2.8 Newton for mm square. So we know what condition it has to fulfill, that is tau V is less than tau C max by 2, hence it is okay in shear. So let us check, tau V is 0.178 Newton for mm square, and you are with respect to this table, tau C max is 2.8 Newton for mm square, but we require tau C max by 2 to say your slab is safe in shear. So tau C max by 2 equal to 2.8 by 2, that is 1.4 Newton for mm square. So hence it is safe in this condition. Next we will check one more condition based on the tau C and tau V relation. So for to calculate the tau C value, we should know what is the percentage of steel and required, and what is the grade of concrete. So from this table we have to calculate, as we are bending the slab, you know at the supports we have to 50% of bar should be bent. The total area should be divided by 2 at the support. So steel area at the support must be ASTS, that is a steel area at the support, that is half of total steel area provided in the slab at the support, that is AST by 2. That will be area of steel at the support must be 241.5 mm square. I think you get this in point. Here at the support of the slab, we are bending the bars at a distance of 1.L from the face of the support into some bends. The 50% bar are one side and 50% of bars are another side. So both the side we have to bend at a distance of 0.1 into L times. That's why the number of bars going to the support is 50% of total bars. So we have to take 50% of total area. That's why I am dividing it by 2. So corresponding to this, we have to calculate what is the percentage of steel is. So 100 into the area is 241.5 into 1000, that is B, and effective depth is 140. According to this, we will get PT equal to 0.17%. To find the tau C value from the table number 19 of IS 456 2000, the value required is, that is PT and grade of concrete. Here PT is 0.17, that is the percentage of steel, and grade of concrete is given as M20. Based on this, we have to calculate what is the tau C is. So here we have the values for 0.15 and 0.25. We don't have direct value for 0.17. If we interpolate like this, the tau C value will be obtained. The tau C equal to 0.28 plus 0.36 minus 0.28 whole by 0.25 minus 0.15 whole multiplied by 0.21 minus 0.15. After that, calculating this, we will get tau C equal to 0.328 Newton for mm square. So to say our slab is safe against the shear, it has to satisfy one more condition, that is your nominal shear stress must be less than or equal to K times tau C. This K value depends upon the overall depth of the slab. The overall depth of the slab values are given in code as our IS 456 2000, the class number 40.2.1.1. So this is the overall depth of the slab, and these are the corresponding K values. Our overall depth of the slab will be 165, but that is in between 175 and 150. So our value lies between these two values. For 175 we have 1.25, for 150 we have 130. So our value lies between these two. I am approximately assuming K value is 1.28 for overall depth of slab is 165 mm. So then you have, for calculating tau c, you should multiply it 1.28 into tau c, obtain 0.328, then we will get 0.41 Newton for mm square. Now see here, the 0.178 Newton for mm square is for tau v value, and 0.41 Newton for mm square is K into tau c value. So our tau v is less than K into tau c. It is clear from these values. So hence I can say our slab is safe against the shear. Then we have to check it for development length. So to satisfy this criteria, so development length LD must be less than or equal to M1 by VU plus L0. You know that M1 is a bending moment, it is section under consideration. That is all the bars which what were provided, they must be fully stressed. That is up to the 0.87 Fy. V is a shear force at the section. L0 is the anchorage length. So we can calculate LD equal to 0.87 Fy 5 by 4 into tau BD. From that you can calculate what is the LD values, that is 470 mm. If you substitute all these values, you will get LD equal to 470 mm. We have to provide in the slab. So this value must be, the LD value must be less than these values. So that value we have to calculate M1 by V plus L0. So M1 is a moment of resistance at the supports. So this M1 we have to calculate with respect to the 50% area of the steel which are going into the support. So the area is AST, so the formula will be like this: M1 equal to 0.87 Fy ASTS into D 1 minus Fy ASTS by FCK into BEC BD. You know what is the ASTS? Is the area of steel provided at the supports. So according to that, M1 can be calculated 11.76 into 10 power 6 Newton into mm, and VU already we know that 24930 Newtons, and hence we are no hooks are provided. Directly we are inserting into the support. So M1 plus VU plus L0 will be M1 is 11.76 into 10 power 6 and VU will be 24930, and so no hooks are provided, so anchorage length will be 0. The value is 471.72 mm. Hence our LD is less than M1 by V plus L0, hence it is okay in the check against the development length. So after obtaining all this value, let us see what detailing, reinforcement detailing is. So as we know that our slab, we have designed a simply supported slab. That means this slab which we are designed is supported over these two supports, or I can say two walls, and the clear span between the support this slab is 3500 mm, that is a LX, and we have calculated, we are assuming 10 mm bar, and 10 mm bar can be used at a spacing of 160 mm center to center. So this line, this is a horizontal line, what you see the black color, that will be main reinforcement in shorter direction. The spacing of the diameter of that bar will be 10 mm, and spacing should be provided 160 mm center to center. And these circles are showing you a distribution reinforcement. For the distribution reinforcement, I am assuming 8 mm dia, and there the spacing should be 250 mm center to center I had provided. And these are the bent bars. I already told you that among the main bars provided, there should be bent 50% of bars in this direction and 50% of bars in this direction. So the benting should be start from 0.1 times L. So total length is 3500, 0.19 times L is 350 mm. From the face at 350 mm, then we have to bend our main reinforcement like this. So this is one more, your what do you say, a cross sectional. This is the main bar in this direction, and this is the main bar in this direction. It will be bent here and here, and if we cut the section XX here, that will be a sectional view of this slab here. This will be a sectional view. Okay. Then we have some quiz questions. The maximum percentage of reinforcement in case of slab is limited to, generally that is a 4% of gross cross sectional area. The analysis of slab spanning in one direction is done by assuming it will be a beam of 1 meter length, 1 meter width, or 1 meter square area, or none. Generally, for designing this, we are considering 1 meter width of a beam. We are considering. So answer will be B. And then third question will be diameter of a bars used for main reinforcement in slab may vary from 224, 426, 8 to 12, and 420, 18. The main diameter bar should be in between 8 mm to the 12 mm. So this is the answer is 6, but it should not be more than, that is 1/8 of thickness of the slab. That condition also will check. So diameter of bars used for distribution reinforcement in slabs may vary from 2 to 4 mm, 4 to 6 mm, 6 to 8 mm, and 8 to 12 mm. Generally, it will be vary from 6 mm to 8 mm. So option C is correct. So thank you. Let us just summarize what are the things we have discussed. As we decided to design a one-way slab with a simply supported ends. For that, we have calculated what is the effective length, what is the effective width, or effective depth, or the total load to be buried. Based on that, what is the total bending moment it has to resist it, and what is the area of tension reinforcement, or area of reinforcement provided, whether it is a suitable, whether it will be safe against the codal provision or not. Those things we have discussed, and we have checked all checks like deflection, shear, and development depth also. So that's all for today's lecture. Thank you.